All right, so we have on this page 4 graphs and we have functions. And what we're going to do is we're going to find the dependent variable value. So in this first one, that would be the miles, and we'll find it for each of these t values. And then we're going to calculate this average rate of change. And we're going to see what the trend is with that average rate of change and use that to decide if our function is concave up or concave down. So let's start by getting these values here. So when t is 0, d is going to be also equal to 0. And when t is 2, it looks like we are going by 50s over here. So it looks like d is 50. At 3, it looks like d is 100. And at 5, it looks like d is 300. And then remember to find our average rate of change. We're going to do our dependent variable subtracted over our independent variable. So for this particular function, we're looking at d2 minus d1 over t2 minus t1 to calculate that average rate of change. So I'm going to do that for these two here. So the difference in d is 50. And then the difference in t, so 2 minus 0 is 2. That gives me an average rate of change here of 25. And between these 2 points, the difference here, 100 minus 50 is 50. And 3 minus 2 is 1. So that average rate of change is 50. So we know it's not linear because these two are not the same, right? So if they were the same, then this could be a candidate for being linear, but it's not since these are different. So let's get our last one and see if we have a pattern here. So 300 minus 100 is going to be 200 over 5 minus 3, which is 2. So that gives me an average rate of change of 100. So what I notice about my average rates of change is that they are increasing. And if my average rates of change are increasing, then my function is concave up. And also from this table, I can tell whether this is increasing or decreasing. So if I look across here at my dependent variable values, these are all getting bigger. So this function is increasing. And the good news is that matches what we have here on our graph. So looking at this graph, we see this is the bowl shape, so the concave up, and it is increasing. So that is how this works. What I'd love for you to do is to pause the video and try numbers 4, 5, and 6, and then we'll come back and work on those together. All right, so hopefully you took the opportunity there to pause the video, try this out so that you feel confident about this skill, because this is something that you can be asked on the test. You wouldn't be maybe given a picture, you'd just be given a table and asked to figure out if it is concave up or concave down just from that table. And to do that, you're going to want to make all 3 of these calculations. So here, my difference is 150. And 2 minus 0 is 2, so that gives me a slope of 75, or an average rate of change there. 175 minus 150 is 25, and 3 minus 2 is 1, so I have an average rate of change, or a slope of 25. And then here, 200 minus 175 is 25, and 5 minus 3 is 2, so when I divide that, I get 12.5 for my average rate of change. And now these are going from left to right, like they would on the graph. As I look at these, I go 75, 25, 12.5. So my AVR, my average rate of change, is decreasing here. Okay, which means that my function is concave down. And then without looking at this picture, I can tell that my function is increasing because if I look at my dependent variable values, these are getting bigger as I go across here. So this is increasing. And if I look at this picture, I see I have part of the umbrella, which is concave down, and these function values are increasing. So we have correctly figured that out from our table. All right, so number 5, these are the function values I got for that. And let's find our average rates of change here. So 2 minus 4 is going to give me a negative 2 over 4 minus 0. So that gives me a negative 0.5. 1.4 minus 2 is a negative 0.6. 6 minus 4 is 2. So when I divide that, I get negative 0.3. And then 0.75 minus 1.4 gives me about negative 0.65. And that'll be over 10 minus 6, which is 4. I divide that, I get negative 0.1625. And as I look at these average rates of change, so negative 0.5, negative 0.3, so these are getting closer to 0, right? So we started more negative, we're getting closer to 0. So our average rate of change is growing or increasing here. Okay, when that happens, we know our function is concave up. And then without looking at this picture, we can tell that it's decreasing because our dependent variable, which is a, is getting smaller each time. So it goes from 4 to 2 to 1.4 to 0.75. So I have decreasing concave up. Right, and then the last one. So this one is about melting ice cubes. And my function values here, I got a 4, a 3.5, a 3, and a 0.5. As long as you got somewhere in that ballpark, you should be fine. These calculations don't have to be, especially like in here, these might have been tricky to figure out. They don't have to be perfectly exact as long as you're close. You should still be able to see this pattern here, that it is those AVRs are approaching 0 and therefore increasing. All right, so let's do this last round of average rates of change. So 3.5 minus 4 is a negative 0.5. Over 4 minus 0 is 4. So I get negative 0.125. 3 minus 3.5 is a negative 0.5. Over 6 minus 4 is 2, so negative 0.25. And then 0.5 minus 3 is a negative 2.5. Over 10 minus 6, which is 4. And that comes out to be about negative 0.625. So my AVR, so I started at negative 0.1, negative 0.2, negative 0.6. So those AVRs are getting more and more negative. So my AVR is decreasing here. And if that's the case, my average rate of change is decreasing. I have concave down. And these dependent variable values are all getting smaller from the one before, so decreasing. The decreasing concave down on the melting ice cube. All right, so when you're given a problem like this with just the table, these are the kind of calculations I'm expecting you to make, and a little note about that AVR would be great.